Research is hard. Probably everyone watching right now experienced this at some point, and this series of videos is intended to make following recent research in the world of vector addition systems even just that slight bit easier. This video specifically is part 1 of a 7-video series about the GVAS reachability problem. The first video is addressed to a slightly larger audience, in the sense that for this video I only assume that the reader is familiar with context-free grammars but might not be familiar with vector addition systems or GVAS. It is intended to provide a good overview on the algorithm for GVAS reachability while removing details. The next videos will then go into said details and are more specialized. Now, with that out of the way, let's dive straight in. So I've prepared a presentation, but for the most part I will actually be writing. Or, well, I guess it's like 50-50. Okay, so in this video series we explain how to decide GVAS reachability. Now, the algorithm is a complicated mosaic of many puzzle pieces, and first you have to define all the pieces and define how they properly fit together, and only then can you really dive into the details. So this is what we're going to do today. We're going to slowly define everything, and then I can actually explain the structure of the algorithm already in this part 1. So, more specifically, the table of contents for today is background on CFGs, definition GVAS plus reachability problem, deciding Z reachability, a tool to decide reachability, and finally a sufficient condition for reachability and the corresponding algorithm this leads to. As already mentioned, this video 1 suffices to understand the structure of the algorithm, and videos 2 to 7 will describe the pieces in more detail, the pieces of this complicated mosaic. Okay, background on context-free grammars. So I assume the reader is familiar with context-free grammars, but just to like fix notation, we have a set of non-terminals that is called V, we have an alphabet sigma, we have productions P, and we have a start symbol S. So for example, this is a context-free grammar. S derives two A1s, A1 derives two A0s, A0 derives A or B. And then in total, this accepts 16 words, namely it accepts the language A or B to the 4. And then the second is a more complicated version of the same, but let's explain how we actually arrive at it. So if we look at the structure of how these non-terminals depend on each other, it would be something like this. S produces two A1s and A1 produces two A0s. Well, we don't like this structure with 2's, and we would also not like it if two non-terminals were able to call the same non-terminal. So what we're going to do is we're going to create a tree-like structure. So we let a non-terminal remember the sequence of decisions it has seen. So for example, here we write L because this is the left side of the first derivation, and R because it's the right side of the first derivation. And then for everything that has already seen some path P, well, it can now go to A0 and it appends where the corresponding A0 is seen. And if you're wondering how is this done for a general grammar, well, here at single non-terminals in general, these will stand for SCCs, but first we have to define what an SCC in a context-free grammar even is. So, a set of non-terminals is called strongly connected if for all non-terminals in this set, it is possible for the first non-terminal to reach the second one, and the other way around. And then an SCC is called branching if some non-terminal or every non-terminal, these two definitions are equivalent, can produce two copies of itself. Just as here above, we do not care about what the dots are. This could be other non-terminals, words, etc. It does not matter. Okay, and then there's one particular subclass we will in the following look at in these algorithms is called fin. A context-free grammar is fin, or this used to also be called finite index, if no strongly connected component is branching. So the examples you have seen on the last page, they are fin. But what's not fin is the typical example of a context-free grammar producing the bracketing expressions. This is very much not fin. This is the prime example of something that is branching. If you look at this rule, it produces 2s, so this is exactly the structure that we have here. Okay. And well, then we have the opposite of fin, or kind of the opposite, which is top branching. a context-free grammar is top branching if the strongly connected component containing the start symbol is branching. So for example, this one is branching. This one is top branching. Well, it only has one SEC, so since it's branching, it's top branching. And then, well, any CFG can clearly be written as, well, I like to view it as some kind of a thin stuff on top of something that is top branching. So if we go back to the tree structure, if you imagine your context-free grammar as a tree structure, then there will be some topmost non-terminals that are branching. Say these guys are the highest branching guys. If these are the highest branching guys, then the corresponding grammars here and here, this will be two grammars G1 and G2. These will be the lower guys, and then there will be a thin guy on top, and this is the thin guy on top. So we like to view the grammar as having a thin guy sitting on top of something that is top branching. This will, well, come in handy in the next parts. In this part it will not happen too much, but I wanted to like introduce the full prelims at once and not in 5 parts. Okay. So this was prelims on context-free grammars. Now we can finally start with the real stuff, with one of my favorite problems, if not my favorite problem. Well, no, it's actually definitely my favorite problem, the GVAS reachability problem. So what's a GVAS? A GVAS is a context-free grammar where the set of non-terminals is contained in ZD. And now if you have such a context-free grammar, then you can interpret its words as paths in ZD. You do this as follows. Imagine you have sigma, which has these two letters in it. Now, whenever you read 1, 2, you imagine that you take a step in this direction. So, for example, you twice take the letter 1, 2, then you take this path. And now next, you could take the letter 0, 1, you would go downwards and so on. And so whatever word you have describes some path in ZD via this sequence of, we call this updates. And observe that the path is supposed to start at 0. We will formally define this in a moment. Okay, namely, a path or a word is valid if it starts and ends in 0 to the D. So for example, this is not valid because this is not 0, 0. It can be derived in the context-free grammar, and the path has to be contained in the non-negative quadrant. So that's the reason why I only drew one quadrant and didn't draw the other parts. Theoretically, you could reach the other parts, but then the path is invalid. We are searching for a path that is valid, so fully contained in ND. And then, well, okay, maybe as first example, this one here cannot produce any valid path simply because the first condition is already problematic. Once you take any transition, you cannot get back to 0, 0. But of course, there are more interesting GVASs. Okay, yeah, because this problem is not nearly that easy. Okay, definition. The GVAS reachability problem asks, given a GVAS, context-free grammar, as I said, with the sigma being a part of ZD, the question is, can we derive some valid path? Well, let's start with some more interesting examples of GVAS. So, well, we already saw the brackets before. So this here, if we call the bracket non-terminals +1 and -1, then this here is now a GVAS. A GVAS with one counter, we say, because the terminals are in Z to the 1. And we see here that actually every word that we can derive is in fact valid. So if you can derive a word, then it has to produce 0. And if you can derive a word, then it has to always be non-negative in the middle. So in this case, actually all derivable words are valid. Again, this is usually an easy case. But we can also have a different grammar. We could have this grammar. And now you might say this does something completely different. Well, actually it does not. So this allows exactly the same words as above. The reason is that, well, we have the restriction 3 and restriction 1. And well, these are actually exactly the two restrictions that the bracketing language enforces, the Duck language enforces. Accordingly, yeah, these two GVASs are actually equivalent. Yeah, not easy to see, but they are equivalent. Well, not easy if you're just given random grammars and not easy grammars. Okay, so now we get started on the interesting stuff. So the first interesting stuff is what's a Z-run. So a Z-run is a path that fulfills the first two conditions. So it has to start and end in 0, and it has to be derivable in the context-free grammar. But it's allowed to go negative. This is the reason why we call it a Z-run, because it may visit negative points. So it may visit arbitrary integers. And now, well, the first thing we have to observe, checking for Z-runs is easy. So, well, this is going to be our first proof. So let's get started. So how are we going to do this? Well, the first thing we are going to need, the first ingredient, is called Parik's theorem. So Parik's theorem states that the Parik image of a context-free language is effectively semi-linear. And then there's a second ingredient we need. Well, it's kind of obvious, but since you can express that a path is supposed to have effect 0, since you can express this as an integer linear program, or as a system of Diophantine equations, we get that in fact a Parik image of this is also semi-linear, effectively semi-linear, but I did not write it as it would cause a line break. Okay, and now we claim that in fact to check whether there is a Z-run, it suffices to check whether whether the intersection of these Parik images is empty or non-empty. So why is this? So the main thing you have to observe is that Parik image of 0 to 0 is closed on the permutation. So how are we going to use this? Well, so there are two directions. First of all, assume that this is non-empty. This is the interesting direction. So if this is non-empty, then there exist some words W and W prime, which have the same Parik image. And W is in L of G, and W prime is in 0 to 0. And now we have to prove that actually the intersection of these two languages, which is the set of Z-runs, that this is non-empty. And well, this is easy, because in fact, W prime being in 0 to 0 means that also W is in 0 to 0, because they have the same Parik image, and 0 to 0 is closed on the permutation. And well, the other direction is even easier. If the intersection of the Parik images is empty, it's automatically clear that the intersection of the actual languages is also empty. Okay, so this way we can very quickly and easily decide whether there's a Z-run. And this is going to be one of our main tools to decide reachability. But let's not get ahead of ourselves. There's still some mountain to climb before we can define interesting things. So the first part of this mountain is called the Steinitz lemma. So people working in GVAS, well, should really know this. Of course, I don't assume anything that you know what a GVAS is. Accordingly, I'm going to introduce this. So what's the Steinitz lemma? And well, I could talk about the formula, but it's really stupid to do that. This is one of the lemmas where the lemma statement is like something, if you write a graphic, the reader understands it immediately, and if you write the definition, he will have to stare at this for 10 minutes. Okay, so the definition is, okay, you take some vectors whose sum is 0. So this means you take such a path. Okay, you take such a path. And now what do you want to do? Well, what you want to do is you want to reorder the path such that it does this. It stays in some smaller block. Specifically, if you look here at the formula, d times the max norm of these vectors, this would in our case be 4. So this means we want to reorder our path such that it stays within this 4x4, within this 8x8 square around the origin. And well, the lemma states that no matter what sequence you give me, I can in fact reorder this such that this will happen. Well, here it was easy. What did I do? I just, instead of walking 3 times in this direction, 3 times in this direction, 3 times in this direction, I just circled here 3 times. Well, yeah, this was just cycling 3 times. Really very easy in this case. Of course, in general, the proof is not that easy, but this lemma is very well known. Okay, what's not as well known, in fact, this is one of our new ideas for the algorithm, is that we can extend this to GVAS appropriately. And here, this is the first location where top branching GVAS make an appearance. We will see in the proof, and we will in fact also see in the further conditions, that this is a very, very crucial assumption for this. Okay, so what does it state? Well, again, I am going to like simplify this, like I'm going to like show this graphically in a moment. But so what's the point? Well, we want to make the above thing, but we want to do it with something that is derivable in the grammar. So what we take is we take a word in the grammar, and we take some cycles in the grammar. And now we want that if we sum all these cycles and the word, then they are supposed to have fx0. But there's one crucial thing. We assume that the cycles use every production. We will see in a moment why this is needed. And then, well, the implication is something similar to above. We want to say there is like a permutation that is derivable. Well, instead of saying this permutation stuff, because then I would have to define what the letters are that occur from the cycles and the W and whatever, and this would cause a notational horror. I just say, okay, there is some words that can be formed by using these. Like, I hope that you can understand approximately what this is supposed to mean. Well, it's supposed to do some kind of permutation of like above of the word that you would produce if you stupidly nest the cycles inside each other. Okay. And then, well, what's actually the claim? Well, the actual claim is that this permuted word W prime that can be formed from this actually remains within, well, before we had this corridor 4 by 4, now it's slightly larger, now it has a factor, and now it has a factor of times logarithm of the number of transitions you want to use. Well, logarithm of this plus 3, but I hope you believe me that the plus 3 is not the interesting part. Okay. Okay, so let's explain this. Actually, I want to draw this by hand because it's just nicer this way. Okay, so how does this work? How are we going to produce this W prime? Well, let's assume we start here with S. And well, let's do the obvious thing. Let's just write W. Right? W is in the language, so there is some derivation tree for W. So now, yeah, actually this also needs to use every production. I should have maybe written this, but okay. Okay, this also needs to use every production. We will see in a moment that we of course need this. Okay, so, or, well, maybe actually not. No, I think it's actually not needed. Whatever. Okay. Yeah. No, I think it's not needed. Maybe let's restart. Um, let's clear the board and try here again. Okay, so we have S. And what are we going to do? Okay, so we have a cycle row 1, and it uses every production. So in particular, it uses something that leaves the top SEC. Well, if it does this, then we can actually make row 1 into a cycle that looks like this. It's a cycle on the starting non-terminal. And so now that we have a cycle on the starting non-terminal, well, we apply this cycle. So we start by applying row 1 here. Yeah, this was actually why we don't need it. We don't start with W, of course. We start with row 1. Yeah, I should really edit this out, but yeah, I think it's way nicer to have a live presentation. So errors are just included in such a thing. Okay, so we use the first cycle, and now we come to the first crucial part. So we said these cycles have to use every production, and for these it's actually necessary that they use every production. Okay, why is this? Well, it uses every production and we are top branching. So this means there has to be some production in here that takes some A from the top SEC and produces A prime and A prime prime. Okay, there has to be some production that produces two symbols from the top SEC. This has to be used somewhere in this cycle. But now comes the interesting thing. Well, now these cycles use every production. So in particular, this means we can take cycle row 2 and row 3, and we can we can ensure that cycle row 2 is of the form A prime goes to something. Yeah, I should have thought beforehand about how to name these, but okay. We're going to have to survive this. And row 3 is going to take A prime prime, and it's going to produce something WL3, A prime prime, WR3. Wow, I should have really mapped this out beforehand. Okay. Well, the point is we rotate the cycles such that they are used at these non-terminals. We can do this because they use every non-terminal. They use every production, and so in particular they use some production of the top non-terminals. Okay, so now we're going to do row 2 and row 3 here. Okay, and then we can argue the same. We can argue that here there will be 2 new non-terminals, and we will put row 4 here, row 5 here. Here there will also be 2 non-terminals. We will put row 6 here, row 7 here, and so on. And well, like this we will go on in a binary tree fashion. And then at some point when we are done with this construction, we pick a random leaf and say, hey, at this leaf I'm going to insert. So, well, we know that these are all cycles, so if I apply all of them, then I still must have my initial non-terminal S. So this means at somewhere there is this initial non-terminal S left. I'm just going to, at this non-terminal S, use the word W. Remember that W is in the language, so I can put this derivation here. Okay, this is a construction you could do. Now, okay, why did I call this tree Steinitz lemma? Well, this is not quite the construction we do yet. There's one important step I did not explain yet, namely in what order do we actually decide upon the trees? Well, there we use Steinitz lemma, normal Steinitz lemma. We take as AIs the effects of our cycles. And then Steinitz lemma tells us that we can reorder the cycles such that if we actually fully use the cycle, then, well, we will remain within this small quadrant. Okay, so what does this mean if we think about the big tree? Well, we are going to decide upon the cycles in such a way that, maybe let's clear here a little bit. I don't know how to delete actually. Well, okay. Okay, I should have checked this before, but it doesn't really matter. Okay, so we have our trees here. Well, maybe let me write a fresh tree. Okay, so we have our trees here, and we have to decide in what order we take the rows. Well, what we are going to do is we are going to take them in the order of in the order that the Steinitz lemma gives us. But importantly, if Steinitz lemma tells us to use, say, row 5 as the initial one, and then next we are supposed to use row 3, then now you might think, well, we put row 5 at first. But this is wrong. It's actually the other way around. If you think about the string, and the last thing it gives you is, say, row 7, then what we're going to put on top is row 7. And now you are going to be surprised and think, what? How does that make sense? Well, you have to think about when do you finish a tree. Actually, where are we going to put row 5? We are going to put row 5 as this tree, because this is the first tree that we finish executing. So this is the first tree that we finish executing. This is the second tree, and so on. And so if you reorder the sequence, then now you sort them in such a way that the lower left child is the first is where you're going to use the first cycle. Then this child is where you're going to use the second cycle. The third cycle is going to be used here, and so on. And so if you do this, then you can now analyze how large your values are going to get if you try to run this. Well, and what you have to understand is, let's say we are somewhere in the middle of this execution. Let's say we are currently here. Okay, how much did we execute? Well, importantly, these are all finished executing. So this means if we analyze which effect we have up to here, well, we know that we had the effect of the first rows, row 5, plus effect of row 3, plus the effect of this guy. And now what's the crucial thing? Well, the crucial thing is Steinitz lemma, and then of course plus some rest. What do I mean by rest? Well, rest is this start before the red thing, this left side of this tree, and whatever garbage is here on the top tree before we started this one. Okay, so now what can we say about this? Well, the main thing we can say is that this whole thing here at the start, this is actually constant. It does not look like it, but it is constant because we applied Steinitz lemma. These trees were sorted according to Steinitz lemma, so this is constant. What's, however, scaling logarithmically is this. Why does this scale logarithmically? Well, how much rest can we have? Well, we can only have rest in one of the trees that's above the location we are currently analyzing. So in these 3 green trees, we could have a rest. Only in these 3 trees here could we have a rest. And this guy, and this guy could we currently have a rest. And well, since we created a binary tree, we are guaranteed that we are in at most logarithmically many cycles. So what's damaging us is, well, logarithmically many cycles, and for each of them, well, whatever the norm of this cycle is. I have not explained what the norm of a cycle is, but you can take any reasonable number, really. And this way we obtain that we can derive some word via this construction, which will remain less than logarithmic. Okay, now I should mention one more thing before we continue. If we go back to the coordinates, one can actually also use this lemma to go from, say, here to here. Like, the lemma is really usable to go from anywhere to anywhere. In this case, what it will say is that you will remain in a corridor around this. This will actually be the kind of view we will use later. And for us, this corridor has a logarithmic size. Logarithmic will become important in a moment. Okay. Well, I purposefully explained this by hand to like slow down, and well, I made a few stupid mistakes that didn't help, but okay, I hope you got the idea. So now we can continue on with, well, first let's see an example of why this is actually optimal. So if you consider this grammar, and you consider the cycle that first takes this transition and then kills one of the s's, if you consider this cycle and you want to use it however many times, well, you are really not able to do this without at least logarithmic value in terms of your counter, because you will have a lot of -1 updates that are before the corresponding +1 update. In fact, if you do the naive repetition of the cycle, so you just like use this cycle here and r times, then of course you would need that the initial value of your counter is at least r, which is even worse than logarithmic. But we have just seen that using a logarithmic tree, we can actually get log 2r. Well, some kind of rounding up or down, but like it's really not about +1. Like this, like we're trying to solve hyper-Ackermann problems. There are bigger things than +1 or -1. Okay, so now to the main part for today. once you understand this, that I can actually explain the actual algorithm. So, sufficient condition for reachability. Well, what do we do? Well, we take a top branching GVAS. Remember, this means well, we had this the whole time, but again, just as a reminder, this means the SEC that contains S is branching. Okay, and we assume three things. First of all, we assume that there is a cycle that what we call pumps the current configuration. What does this mean? Well, this cycle on the left derives some word up and on the right derives some word down. And these words are supposed to be constructed such that using the word up, yeah, I should have actually put the image earlier. Okay, so what happens is up moves you from 0 to something that is and that is greater 0 on every coordinate, and down goes from somewhere else to 0. And the point is down will be derived at the end and up is the start. And so if you have something like this, then the point is, if you want to know whether there is a valid path from 0 to the D to 0 to the D, then you can now equivalently check whether there is a valid path from delta to delta prime. Simply by like if there is a oopsie, no, not equivalent. The important thing is, well, we have the important direction. If we check that there is if we check that there is a path from delta to delta prime, that there is a valid path from delta to delta prime, then we know that there is a valid path from 0 to the D to 0 to the D. Okay, so now we can start with condition 2. Well, you might think this is already enough, but the problem is delta and delta prime are completely different directions, so this by itself is not enough. So we're trying to make them the same direction. So what we do is this: we take a cycle, so we assume that there is a cycle. And now what does this one do? Well, first of all, it has to use every production. This is such that in a moment we can apply the Tree-Steinitz lemma. And second of all, we want that if we sum all the four words, W, W prime, up and down, then we are supposed to have fx0. And finally, well, probably you expected this one as the first, but I like to state it as the last. And we need to have a Z run. If there is no Z run, clearly there is no run either. Okay. And now the conclusion is there is a valid path. Okay, why would this theorem be true? Well, I already started to draw this, and I said that it's enough to check for a path from delta to delta prime. Well, actually, we can repeat this. We can repeat this arbitrarily often. So actually, it's enough to check that there exists an n such that n times delta has a valid path to n times delta prime. And now you're going to ask, okay, but how did this make anything simpler? Now we have these weird deltas which we cannot control. Well, actually, this has just become very simple. I claim the proof is just this. I draw a rectangle. Why is this the proof? Why is this the proof? Okay, so let's think about Tree-Steinitz lemma. What does Tree-Steinitz lemma say? If we go back to the last page. Well, it says we want some cycles and we want a word. The word will be the Z run for us, which together sum to 0. Why do they sum to 0? Well, they don't sum to 0 in our case, but they sum to a path from this node to this node. This is the important thing. They sum to a path from here to here. And then we said, if you sum to a path from here to here, then what you can assure is that you will remain in such a thing which has logarithmic width in the number of cycles you want to use. How many cycles do we want to use? Well, n, where n is the number of times we use the up and down pump. We want to use this one exactly as often as the up and down pump, because then we know that in total they actually cancel out. Okay, so of course at this point still you probably don't see it, but now what do we have to do? Well, let's just check the conditions of the three-Steinitz lemma. So well, there are there are a few conditions. The first condition is top branching. Well, our theorem explicitly stated top branching. So this one we have. Then we have to check that the cycles use every production. Well, we explicitly require that these cycles here that we are going to use, that these use every production. So again, this one is done. We want the W in L of G, and we want these cycles to add together to sum 0. Well, this is given since, okay, W for us is chosen as a Z-run. Z-run meaning it has the effect 0. And then, well, if this has effect 0, then by this equation, using n times W and W prime will exactly cancel out the up and down as well. So in total, we know that actually these actually sum to the required path from red to blue. Okay, and then now we need to check why does this remain non-negative. I mean, at this point, it would be magic if it were non-negative, right? Well, this is where we use the then, of course. Now we can use the theorem. What does the theorem tell us? Well, the theorem tells us that we remain in something that is logarithmic depending on r. But if you look at this situation, we start from n times delta and end at n times delta prime. So the source and the target are at least n on every single counter. So the source and the target scale logarithmically. Meaning the location, these anchor points for the rectangle, these scale linearly in n. These scale linearly in n. On the other hand, the width, as we said, the width scales logarithmically. So this is ln in n. And the width scales logarithmically. But, well, we just want to show that there exists some n where this holds. There exists some n. Well, of course there exists an n where the linear function has overtaken the logarithmic function. So yes, such an n exists, and therefore we know that there is a path from 0 to 0, and specifically the construction that we can do is, as indicated here, we start by taking the pump, which then also means we have to end with the down part of the pump. And then in this rectangle, once the rectangle is fully in the positive quadrant, we take the path that is guaranteed for us by the three-Steinitz lemma. Okay, so now at this point you might be wondering, okay, so we have taken quite a bit of time just to show this theorem. Is this theorem really this important? Yes, this theorem is very much the basis of the algorithm. At this point, I can just tell you the algorithm and you will immediately see why it would work. Or, well, it would work if we could create its subprocedures. Okay, so what's the algorithm? The algorithm to decide GVAS reachability. Remember, reachability means the question whether there exists a valid path. You're given a GVAS and the question is, does there exist a valid path? How do we decide this? Well, we start with our input GVAS, we put it into the work set. And then what we're going to do is we are simply going to create a while loop. And in this while loop, we are going to repeatedly check whether there is some GVAS in our work set which does not fulfill the condition. Okay? So essentially I claim that this condition is decidable somehow. This is magic number 1. We claim this condition is decidable. Now, if the condition does not hold, what are we going to do? Well, we are going to update the... Okay, this is of course stupid. We are not just going to add something, but we are of course going to remove G. Okay, live edits. Okay. Okay. While there exists a G that does not fulfill the sufficient condition, we update the work set by removing G and adding something that is smaller than G. So smaller, if the sufficient condition does not hold, compute some kind of GVAS that is smaller in some sense. Well, a sense that is not defined yet. But then finally, we will, once we exit the while loop, we will return the work set. So let's see, why does this algorithm actually do what we want? So first of all, if this smaller actually reduces a well-founded rank, then this implies that this algorithm clearly terminates. The point is, whatever we replace the work set with always has smaller rank than before. So this is clear. The question is, why is it correct? Well, you might be surprised that at the end we just return whether the work set is 0. Well, this is exactly where this theorem comes in. This theorem tells us that if anything survives in the work set, so if there is at the end some GVAS that fulfills the sufficient condition, remember exiting the while loop means that everything fulfills the sufficient condition. If at the end there is some GVAS that fulfills the sufficient condition, then the theorem guarantees us that there is a path. So in order to decide whether there is a path or not, we just have to check whether this is empty and answer accordingly. Well, of course, what the function smaller has to guarantee is that it did not change the fact whether there was a valid path or not. Well, at this point you can guess what the we have to do in the next parts. What we have to do in the next parts is we have to explain how to decide the sufficient condition. We have to show how to create smaller queries. But this is really it. Well, this was the sufficient condition for top branching. We need a sufficient condition for thin as well. But then in total we are done. Okay, so let's go with an exercise for the viewer. I think if you think about this, it will help you for the next part. So what's going to happen for this condition is that in one of the cases, we will remove a production in the sense that we fix that this production will be used exactly k and n times in every derivation. Say you want to create a grammar where a specific production is used exactly k and n times in every derivation. What exactly happens to this grammar? And why would we claim that the new grammar is smaller? This is one of the things that we would have to do here. We would have to remove a production and then claim that the corresponding grammar is smaller. So up to next time, I would recommend that you think about, okay, why would this be smaller? And how would I even do this? How would I create a grammar that fixes that a certain production is used exactly k and n times in every derivation? Yeah. But so this is it for this time. So as short recap, this is the algorithm. There are only two things we need to do. How do we decide the sufficient condition? How do we create smaller queries if a sufficient condition does not hold? And then the algorithm is clearly correct. So this gives us for next time the following. Yeah, I should have really put the picture first. Okay. So, well, we have two cases of grammars, thin and top branching. For the top branching grammars, which is this lower half, well, I guess I should have made these green since I already colored one of the things green. For the top branching grammar, which is this lower half, well, we have to show that we have to show how to decompose if there is no pumping cycle, how to decompose if there is no different cycle, and well, if there is no Z-run, then clearly you can just reject. This is what remains for top branching. And well, as you can see, I drew here 6 parts. That's not a mistake. This will actually be surprisingly complicated. The decomposition will not be as straightforward as we want. All these 6 puzzle pieces will together imply the decompositions. But okay, that's it for top branching. What we also need, however, is we need to deal with fin. And in order to deal with fin, we will next time deal with a subcase called almost linear. So what we are going to do is next time we are going to look at these three lines, these three puzzle pieces. For almost linear grammars defined next time, we are going to write down a sufficient condition. We are going to explain how to decompose if there is no pumping cycle and how to decompose if there is no difference cycle. And then this will give us an algorithm like before for the class of almost linear. Then in part 3, we will extend the corresponding algorithm to the fin case, giving us the top row of this mosaic. And then, well, the remaining cases, the remaining videos 4 to 7, they will do the top branching stuff. So specifically 4 will show everything, assuming that we can compute some function I call forward ideal. And then finally, videos 5 to 7 will show how to compute forward ideal for GVAS. But either way, I hope that this video has convinced you that GVAS reachability is actually decidable and given you the general theme of how the algorithm is going to work. Starting from next time, we're going to assume a little bit more knowledge on or about VAS. Well, and this is it from my side. Thank you.